Good morning, chemistry fans. Now we're going to get into really the work of acid-base stuff. I mean, we've identified pH and we found different ways either simply to find pH or hydrogen ion concentration, what they mean. We did some ice problems and some other stuff using the acid dissociation constant to tell you whether it was a weak or a strong acid. And again, everything we said about acids was true of bases if we want to do it. Now we're going to move into what acids and bases do together in the lab that we are going to perform, which is a titration lab. The first thing to understand is acids and bases neutralize each other. Now in our world, again, we're sticking kind of with the Arrhenius acid where it starts with an H and the Arrhenius base where it starts with an OH. And then they neutralize each other because you can see it's really just a double replacement that we talked about at the beginning of the year, or when we started doing reactions, and I mentioned this at that time, that then the H goes with the OH and the Ca, the calcium with the chlorine, and you get water and a salt are always the product. And that's why we use the Arrhenius stuff. Doesn't matter what type of base it is, acids with bases neutralize each other. And so using this very simple formula, that's a relationship we can use. It looks very much like a solution, M1V1, M2V2, and it really is. So it's a valuable tool for identification of unknown acids and bases, concentrations, tons of application in medicine and industry based on the fact that acids and bases neutralize each other out. So the lab technique, which you're going to see in tomorrow's video, is very simple, and it's called a titration, and it's an incredibly simple setup. It's just using careful measurements of acids and bases and adding one to the other and using the concentration ratios, again, like the M1V1 relationship we saw earlier, for solutions to determine what was unknown. Determining what an unknown material is, or the concentration of a material, or how much volume you would need to neutralize. Acids get spilled, or bases get spilled all the time in the environment. You know, a truck turns over, a train derails, something goes on, and they have to neutralize it with either, you know, depending on what's spilled, they need to neutralize it out with either an acid or base, how much to use to neutralize it but not harm the environment, all sorts of stuff along that line. It's simple, it's inexpensive. There isn't on a daily basis a procedure used in any science anywhere more often than a titration, and titrations are used in all science at every different level. Anyhow, it goes on a simple point that by carefully adding acids and bases together, which is called titrating, I will eventually get to an equivalence point. Notice where the pH is, right at neutral, where I match the exact number of hydrogens from the acid with the exact number of hydroxides from the base, and they've neutralized each other. You can even notice in the pH range, right when I'm getting near that equivalence point, that notice that it's almost straight up and down, because the closer I get, you know, I'm right in that range, you know, I'm almost using the same amount anyhow. If we're titrating an unknown acid with a known amount of base, with a known concentration, you might recognize it's no different than a dilution. Okay, now it's not diluting a substance, M1, V1, M2, V2, but it's going on the point that you've used the exact same number of moles of hydrogens and hydroxides at the equivalence point. So it's very much like a dilution, because remember, the key to a dilution was they both had the same number of moles, so I could compare them. Same here. If I hit the equivalence point carefully in my titration, then they both have the same number of moles, so I can relate them together. MAVA equals MBVB. The molarity of A and the volume of A will be equal to the molarity of B and the volume of B right at that point, because the moles are the exact same. Okay. So that's why we carefully add stuff so it exactly hits that point. Now, how do I know when I've hit that point? Because as you're going to see when we do the lab, or when I do the lab for you, that you're mixing clear solutions together. You need something to tell you what that is, and that's an indicator. And the most common one that we would use and that gets used is something called phenolphthalein. Phenolphthalein is an indicator that indicates it turns pink in the presence of hydroxide ions. So when I hit that equivalence point, one more little droplet, one more little bit of OH will turn it pink, just barely pink. That tells me I'm at the equivalence point. And again, because of a little bit of buffering range here, I'm okay. You know, that'll be close enough, as you're going to see in our lab. So we need an indicator. Okay. Now, MAVA, MBVB isn't good enough because sometimes you have what's called a polyprotic acid. Or, and I can't think of what the equivalent term, but you can see what a polyprotic acid is. It has two hydrogens at the start. So it has oxalic acid, two hydrogens. Ascorbic acid has two hydrogens. Sulfuric acid, you know, two hydrogens. Phosphoric acid, three hydrogens. Arsenic acid, three hydrogens. And what you can see is the initial dissociation constant. That first acid generally comes off relatively. You can see oxalic acid. Whoops, let me skip. Let me skip back. Oxalic acid is a weak acid to start with, and so that first one comes off fine. The second one, notice the exponential difference, is much harder to tear away. Once you take away one hydrogen, the other one doesn't want to let go because it's being held tightly in that sphere, because now you've lost an H. It's now the anion, the negative anion, is really grabbing onto the hydrogen. Same here with ascorbic acid. Notice it starts as a weak acid. Look at that second dissociation to the -12. So getting rid of that one is hard. Sulfuric acid, if you went back in our videos, you know it says very large because it's like 10 to the 8th. You know, like a million times that equilibrium, it's way up there. But notice that getting the second one off, going from an exponent at 10 to the 8th, very large, 10 to the 8th, 10 to the 9th, to -2nd, it's hard to pull that one off. But it's not hard when you're doing a titration because you're neutralizing. So in all the compounds that are in that solution of all the, say, sulfuric acid, the first hydrogens all come off and get neutralized. Well, then for the equilibrium to balance out, then you got to start, the second one's got to start coming off until you've gotten neutralized all the hydrogens. Or in the case of the phosphoric, okay, the first thing the titration does is neutralize all the first H's on all the compounds. Then it does all the second H's. Then it does all the third H's. What that means, though, is that our formula then becomes not MAVA equals MBVB, but MAVA divided by the number of the coefficient of A is equal to the molarity B, the volume of B, divided by the coefficient of B, which means one of the things you always need in a titration to do the math is a balanced equation, so you know what that coefficient is in front of the number. Okay. All right. So really, this formula and a balanced equation are all you need. And titrations are really plug and chug math. We're going to do a couple here, then we'll actually show you what it looks like in the lab. We'll do a lab with it, of which the calculations are going to be all the same thing, drill and kill. Plus, I'm going to put up some homework here with just a few problems for you to try. Okay. Anyhow, let's look at some samples. Here's the first one. It takes 54 milliliters of 0.1 molar calcium hydroxide, that's our base, right here, OH, to neutralize 125 milliliters of hydrochloric acid. There's our acid. What is the concentration of the acid? So here's my formula, MAVA over NA equals MBVB. You know what? I write it this way. It's easier. I get rid of the division sign. I just flip them over. NB MAVA equals NA MBVB. It's all lined up in one linear shot. I don't care which one you use, whichever one works for your mind easier. I always find the linear works great, but then you have to remember that the ends are on opposite sides. Anyhow, then we have our formula. Calcium hydroxide plus hydrochloric acid makes neutralization reaction water and the calcium chloride salt. I balance it. And now what that tells me is a couple things. Let's list out before we do our formula what we know. We know we're looking for the molarity of the acid. That's our question. We know we have the volume of the acid. It's told to us in the problem. We know the coefficient of the acid because I have the balanced equation now to look at. And that's a 2. I also know what I have here for the base stuff. I know from the problem that my molarity is 0.1. I know that the volume is 54. And I know from the balanced equation that since I didn't write the coefficient there, it's a 1. Now I have 5 variables. I can plug them all into the formula. Okay. And when I do so, 1 NB times MA, that's what I'm looking for, times 125, the volume of the acid, equals 2, that's Na, times 0.1, which is MB, times 54, which is VB. If I do all that math to isolate for MA, it's 0.086. Okay. And if I look at it, it takes twice as many acids to neutralize the hydroxide because this is kicking out 2 OHs for every 1 H. Okay. And I used a little more than twice the volume. So I'm going to guess that this should be pretty close to 0.1, and it was. Okay, that's some of the rationale I can use. Let's look at another example. 10 milliliters of an unknown concentration of hydrochloric acid is titrated with 20 milliliters of a 0.5 molar sodium hydroxide solution. What is the molarity of the acid? Again, there's my balanced equation. Nice balanced equation. Hydrochloric acid plus sodium hydroxide makes water and sodium chloride. Everything's a 1-to-1 ratio. There's my formula. NBMAVA, NAMBVB. I know my A stuff. I'm looking for the molarity. The volume given to me was 10, and the coefficient from the equation is 1. I know the base stuff. It's 0.50. I use 20 milliliters. And the base, again, the coefficient was 1. Plug it into the formula. Okay. 1, the coefficient of my base. The molarity is what I'm looking for. 10 was the volume of my acid. 1 again was the coefficient of the acid. 0.5 was the molarity of the base. 20 was the amount I used. It's 1 molar. Now think about it. It makes sense. 1H, 1 OH. But it took twice the volume here to neutralize it, which meant that, you know, with twice the volume, that was most likely twice the concentration. Right? Okay. Anyhow, that's it. It's very similar to solution math. It really is. You just have to account for the coefficients. But that's how they, and you'll see in the lab, we're going to titrate acids. We're going to titrate bases. We're going to find unknown names. We're going to do all sorts of stuff. Okay. Right now, I would download the few homework problems I have for you and practice those. I believe I put the correct answer with it or somewhere. So the correct answers are, I believe I gave you the correct answers. I may have jumbled them up now that I think about it. But you can solve the problems, look at the jumbled answers and see if you got the right one. And then tomorrow we'll show you the lab video. And then Friday we'll do the analysis of the lab. There you go. Okay. That's all we got for today. Have a great day.